Hi, everyone, and thank you for attending today's seminar from Physics Latam, particularly some seminar part of the General Relativity and Cosmology series course. Today, we are happy to have Nikolina, who is a currently PhD student and researcher at Newcastle University. Her work mainly focused on mitigating theoretical uncertainties for the weak lensing cosmology, which is the topic of today's talk. Thanks for accepting our invitation.
Oh, thank you very much for inviting me. I'm very happy to be here and to share, to spread the knowledge that I spent time understanding. So, cosmology with weak lensing. So it is a particularly rich field of cosmology, and it's an observational. Well, it can be a bit theoretical. It's in the middle of everything, basically. Mostly it's observational, but when I say observational, I don't mean that I am me personally, I will never touch the telescope. It's mostly in terms of we are using data or not, as we're going to see at the end. But in any case, it's a powerful probe that, oh, why is my, there we go. A powerful probe of large scale structure and general structure of the universe, so the content of the universe. So I wrote from observation to results, but actually I will not have time to touch upon all of the steps, how we go from, as you see in the first picture, for some patch of the sky where we are observing galaxies, and then through some data analysis, and then finally getting that plot that you usually see in cosmology papers and archive. Again, I'm repeating, if you at any point do not understand what I'm saying, please ask Daniel, send Daniel a DM, and then Adana is going to ask for you. Okay, so the aim of this lecture is just to give you a general overview of what this weak lensing cosmology is. And I'll try to give you some basic concepts. Of course, I will have to touch upon some mathematics, but not too much, so don't worry about, being strictly filled with formalisms. I will try to give you practical information. And lastly, when I show you these slides, I didn't have time to include it currently, but when I send it to Daniel, you will get some resources that I think will be helpful, being that some code that is available that you can, play around for free, or some libraries that you can install, or basically first to tell you which libraries are used in this line of work, or books or primers on the particular topic. This lecture is based on the lectures of Ami Choi, Daniel Leonard, and Dragan Huterer, and some of my previous lectures. So some of things I'm going to present are adapted, some of things are verbatim taken from these lectures. So I just want to make sure that you are aware of that. And of course, I will share the links to these talks by Dragan and Ami. Danielle's talk, unfortunately, is not available outside of our collaboration. But in any case, I'm going to just give you, you're basically going to just try to dip in our toes into this magic pool of weak lensing cosmology. So most people start with these pictures, this pie chart where it says the content of the universe. So this is what we are particularly interested in as cosmologists, how much of stuff you have there and what kind of stuff is there. So usually you get these results of massive surveys, like for example, Planck, how much of that, of the universe is actually the baryonic ordinary matter, how much is you have the dark matter and dark energy. And these contents, we represent these fractions of certain types of matter or ingredients of universe with these omega, right? So omega lambda is for the dark energy, then C is for cold dark matter, B is for baryons. And then maybe you have, depending on the model, if you have curvature, in theoretical model, then all of them, when you sum them up, they will equal to 1. Right? But in this case, we are pretty much certain, the data is showing us actually that we are living in a flat lambda CDM. So flat means that it's flat, the curvature is 0, and lambda CDM, so it refers to the lambda is the dark energy component and then cold dark matter. it seems that this is the case. This is the reality. Now, there are several ways in cosmology you can play around with stuff, right? You can do simulations. So you use some sort of models and then you simulate it on a computer. You can do observations. You can do theory work. And then, of course, you can choose a particular time of evolutionary period in the time period in evolution of the universe. And then you can focus studying that. So that means you can work in inflationary cosmology, that means early universe, right? Or for example, you can work what we call late time cosmology, which is what I do. So when you're actually studying clusters of galaxies and galaxies in, when the galaxy is already formed. So basically you're studying universe as a whole in both cases. However, you're studying from different perspective, right? We are looking how it is now and then try to extrapolate further back, whereas the people that work in the early universe do exactly the opposite. And then, of course, you can choose different things to study. So if you're studying in early universe, you can observe the CMB. So basically, you're working with photons. We're also working with photons in a way, but we are observing these galaxies, right? The structure, how matter is distributed in the universe. And the things you want to answer, for example, what is the geometry of the universe, right? Or what is the expansion rate of the universe? You want to know what is the distribution of matter. And does it match? So, for example, if your theory or your model, whatever, does it match what we actually observe? There are particular probes that can give you answers about the geometry, being that the distances, because distance is a very crucial component, and it's really tricky to measure actually in the universe. So when I say the geometry, I do mean not just the flatness or non-flatness, but also the distances and so on. You can use CMB, you can use BAO. Does anybody know? Sorry, I can't see your faces really. BAO, is anybody familiar with that? Sorry, I have to use these acronyms. BAO stands for baryonic acoustic oscillations. So you can look into that. You just try to find a Wikipedia page first, and then I can provide some resources. SN stands for supernovae. So supernovae are more a topic of astrophysics. However, we absolutely need supernova information in order to understand distances or to find out distances. And supernovae type 1A are the standard candles in cosmology. If you want to learn more about it, you can maybe look up the distance ladder, cosmological distance ladder, and then you will understand how it works. But on the other hand, there are probes that will give you more insight, not just about the geometry or the distances, but also the growth of structure, which is what we really want to know, because you want to know how much of matter there is, how it is distributed, and how it is expanding, for example. And you can use this particular gravitational lensing to answer that, but you can use other probes like cluster abundance, or RSD stands for Redshift space distortions. Something very cool, a very nice technique. So what I'm going to talk about is this gravitational lensing. So I'm trying to ease you into and to tell you that this gravitational lensing is a very powerful way that can give us the answer to how much of stuff there is in the universe, how much dark matter, dark energy, and so on, and how is this matter distributed. So to start off with this gravitational lensing business, so let's assume some sort of geometrical situation that I drew here. So if we are here, can you see my cursor, by the way? Okay, so we are the observer, this big eye here. And this is our plane, right? We're observing some stuff in the sky. Now let's think about a situation where you have some distant source of light, some galaxy. So when I'm talking about the sources, it's galaxies, right? I don't care about, as cosmology, we don't care about the stars particularly. It's just well, I should not say, not in the same sense, like we are not measuring stars, we are observing galaxies. Because stars are very important for cosmology as well, but not in that sense. So sorry for the derailing. So let's go back to the main point. So the situation is we are observing some sort of source galaxies. So we have very distant galaxies in the background. But between those galaxies in the background and us, there is a large clump of galaxies, or cluster of galaxies that are in the foreground. We say they're foreground galaxies. So for the sake of, just so we're going to use these words a lot, sources and lenses. So the lens galaxies are the ones that are between us and the source galaxies. So lenses, sources, right? And then we have the line of sight. So basically the lens galaxies are blocking our view of the source galaxies that are behind. Is that clear? Everyone, can you thumbs up? I mean, this is pretty trivial, right? You're already in physics, so you should. Once again, source galaxies in the background, foreground, lens galaxies. Now, what is gravitational lensing? In very simple terms, it is a deflection of light by very large structures along the line of sight. So now we are looking basically further from when you're looking into the screen, right? And there are some sources in the back, so source galaxies, they're emitting light. However, between the sources and us, as I said, there are these lenses, galaxies that are in a cluster. So it's a huge amount of mass. And as you already probably had some GR courses, you know that what's going to happen is that the light is going to, well, follow the geodesic, right? But because there's a lot of mass there, you're going to have a lensing effect, right? Your mass is going to act like a lens. So the light is going to be deflected. So basically you will see the light from the galaxies from behind. And there's a really neat effect because you not only are you going to be able to see these galaxies, they're going to be slightly modified, which is super cool and super useful for a cosmologist. Is this clear? Is everyone like on the same page here? Everyone understands what's going on? Can I get some thumbs up? Okay. Right. So now we are doing a bit more. Sorry, I'm really moving this Zoom thing around, trying to. Right. So to start a bit more serious. So I drew this diagram here of the situation with some angles, right? We need to use angles. We need to use some trigonometry to help us, or geometry to help us with this problem. Bartman and Schneider have this, I don't know, 300-page primer on this with cleansing and stuff, and they really go into detail. So if you're really keen on deriving stuff, I would suggest maybe using that book. However, I personally I'm not a fan of the picture they had. For me, it was the easier to understand the situation by using a Wikipedia, whoever did it for Wikipedia. There is a diagram. It looks exactly like this. I only changed a little bit the notation. So it is the same situation that I said again. So before, sorry, is the observer. We're observing some sort of galaxy here. However, and then we have a big cluster between us and this image. However, in reality, the source is not at the position where we're observing it. And then you can have some angles. So you have a theta angle is the angle of our observed image, right? And then you would have alpha and beta. Alpha is going to be the angle of deflection, how much is deflected from, so the source, the original thing from the image that you see. And then you have beta, which is the unlensed position. So you have to think about, and then you have these like psi and eta. Those are like position vectors. So you have to think about them in terms of vectors. So theta is alpha plus beta, right? And then you'll have dl. So this is the distance to the lens. You have the distance between the lens and the source, and then you have the source distance. These distances are moving distances. So, sorry, I think it's the angular diameter distance probably. So it's not just a regular distance, right? You have to work in cosmological terms. Right. And then this alpha angle actually can be, right, you can define it also here because trigonometry is really cool. So keep that in mind, this reduced deflection angle. I will not spend more time on this, but I think this image is going to, or this plot is going to repeat several times over several slides. But I would suggest to, when you have the time, work it out yourself, just like draw the situation and then try to derive all of these things I'm going to tell you, because it's useful once you do it, and then you're fine. Okay. So the lens equations, as I said, is we just tells you that the theta, so the observed angle is just sum of the beta and alpha, right, of the lens and the real angle. But you can also define this this reduced deflection angle alpha hat as the alpha times the distance to the source, so this here, over the distance from lens between the lens and the source. And you can combine, you can now relate that thing to a point mass, basically. So you're going to have some sort of mass here with some constants over this vector, and then another constant. So that's a really cool thing. So you already see that just by using the simple trigonometrical or geometrical problem, you can relate angles, so observed angles or deflection angles, and the distances to mass. And this is already giving you intuition, right, that this is very useful in terms of cosmology. Same situation here. Now what you can do, you can use a very thin lens approximation and a Born approximation, so which tell you basically that the deflection is very high. If basically that you can, when you slice this, when you imagine a plane there, is deflection is very high there, but then it really drops off when you go further away. And then when you apply these things, a Born approximation will tell you that you can basically integrate over when you stack all of these things in this way with when you're integrating over this side. So you will not just get a point mass. Right now you can actually extend it to the real thing. As I said, I'm not going to spend more time on this. I would really suggest just going through Bartleman Schneider once for yourself. Okay. And now it's really cool. You can play around and you can construct some sort of, how would you call it, quantities that are very useful in terms of what they tell us. And one of these is called the surface mass density, and it's kappa, and it depends on the angle theta, right? It's the total, the observed angle. And it gives you, sorry, it's dimensionless because we are having this the dimensionless, sorry, the surface mass density in this dl theta over some critical. And this critical surface mass density is just defined in this way. You have some sort of constants, and then it's literally the distances to these objects, right? The distance to the source over the distance to the lens times the lens source distance. When you construct this quantity in this way, just a second. Then you can say, okay, what happens if this surface mass density, this top one, is greater than the critical, or vice versa? What happens? And this is why we do these things. So then you have two regimes. So if your kappa is less than 1, that means that your, did I make a mistake? Okay, this is a mistake. I think I made a mistake here, for sure. When kappa is equal to 1, it's a strong lensing regime. but the critical is not greater than the other one. Whatever. Can somebody can, if you have the time, you can correct me, but I think I'm right. In any case, you just flip the signs for the surface densities. But if kappa is smaller than 1, the critical density is larger, and you have a weak lensing regime. So maybe it's still you are not. It's not clear what it means, this strong lensing and weak lensing. But I'll tell you in a second. So you can think about these. Just go back to this image here, and this is a pure geometrical problem, right? So you have a source here, and then suddenly, actually, what you see in the image is here. So you have just a transformation of coordinates, right? And that is very straightforward to do in physics and maths. And that means that your transformation is going to have some sort of associated Jacobian to it, and it looks like this. And then when you expand it, you write it down, you're going to see that it has 2 terms. There's this kappa term and this gamma term. And kappa term is called convergence, and gamma is we call the shear. And here phi, I just said that this is the angle between the x-axis and the angle alpha. Alpha is the deflection angle, if you remember. But bottom line is, without all this math, so just remember that we are doing, because it's pure geometry problem, and it's a transformation of coordinates. What will convergence do? If convergence is in this Jacobian, if convergence is stronger than the shear, you're going to have the strong lensing regime. And what it means physically is that your image is going to be magnified. Shear, on the other hand, well, the word tells it, I don't know if you know in English, shear means it's stretching. So your image is going to be stretched. The thing is that the strong lensing, you can see it with your eye, and I'm sure that a lot of you saw these fantastic, beautiful images from Hubble, where you have this, well, the image is also stretched, but it's magnified, so you see this, for example, Einstein cross or something, right? So the image of the galaxy that's behind the cluster, excuse me, is beautifully magnified and stretched. But that's a strong lensing. The weak lensing is the one that stretches the image and you can't really see it. It's a really small effect. So this talk is dedicated to this weak lensing regime. I don't work in strong lensing. I'm not going to talk about it, okay? So let's move on. So in weak gravitational lensing, what is stretching, right, is shear, can, if you imagine some sort of mass, for example, here in the center. So the image, if your light is traveling around that mass, if the region is underdense, so there's less, right, it's like a void or something, your galaxies are going to align in this way, like just imagine it like this, like a flower, like radially. If it's overdense, it's going to align in this way, tangentially. And then B modes is after at the 45 degrees. With gravity is doing this E modes, and it's a bit complicated, but just to explain, however, think about it in these simple terms, how it is, just the shape of the galaxy, how is it stretched along which axis, right? Is it radially or tangential? And what we want to observe, so let's just imagine that galaxy, what we observing, the ellipticity of galaxy, right? Ellipticity you just know from geometry, right? You have the ellipses. So galaxies come in all sorts of shapes and sizes, but let's just assume that it's some sort of, it can be a spherical or ellipsoidal object. And I mean, even a sphere has a certain ellipticity to it, right? So you can say that your observed ellipticity is then what you're observing on your survey, on your images. Your galaxy is a combination of its intrinsic ellipticity and then this effect, this extra that is coming from shear. However, if you would do that on one galaxy, you can't use this equation because you would need to know this intrinsic, and you can't really do that on one galaxy because how do you know what is the intrinsic shape of that galaxy, right? So what we need to do is we need to use a clever approach, and cosmology is giving us that. It's called cosmological principle. And where you know from observations that on large scales universe is homogeneous, is isotropic, and stuff is pretty random. So this randomness is a key thing here. So if you would take and sample a lot of galaxies everywhere in the sky, or as much sky as you can cover, you know that galaxies should be randomly distributed. So then you can sample your average observed ellipticity, and then you can assume that the intrinsic one is going to vanish, it's going to be zero, right? It's going to average up to zero. And then what is left is your shear. And that shear, as I said, is connected to your, actually you can connect it to the mass. So you would, like if you have a patch of sky where you manage to sample the galaxies, then you can fairly, with pretty big confidence, say, okay, it's going to be more or less the same everywhere, so I can average it out. So it's really, you need statistics in order to do this. As I said, you can't do it on one galaxy, like it's in the case of with strong lensing, when it's really just blown up image. However, on top of this very small effect of this shear, we can say this zero, right? But when we are actually modeling, we know that there is something called intrinsic alignments, and I work on that. It's a systematic. How if some galaxies, like source galaxies, are locally in some sort of potential, gravitational potential field, on top of the intrinsic, what the ellipticity, they will be intrinsically aligned locally in that cluster. Right? So on top of this really tiny effect, you have another even tinier effect, intrinsic alignment, that we need to understand how they are aligned locally, so that we can detangle the intrinsic alignment from the shear and so on. But in any case, I'm not going to spend time talking about the intrinsic alignments. Just think about that. You just have to average, sample a lot of galaxies, so that means hundreds of thousands of galaxies, millions of galaxies everywhere in the sky, and you assume that you observe some sort of ellipticity. You assume that their intrinsic one is going to vanish because of the randomness, and then what you're left with is this shear. Okay, so this is more or less just a little bit more theory. So what were we measuring, right? We said we are observing the shapes. We are observing the galaxies, and surveys, they can be, well, spectroscopic or photometric. So if it's a photometry, you're going to get like images of galaxies, right? So you have to have very clever ways of reduce the images and then try to see what is the shape and then count it everywhere in the sky. So if this is like two galaxies that are somewhere in the sky, and then there's an angular distance between them, you're measuring the shape of one related to the other, right? And then the shape of the other, this one to this one, this one to this one, and so on. But every time you're working in pairs, right? As I say, you can't do it on one galaxy. You have to correlate one galaxy to the other. And this is the basic of the method called correlation function, right? It's just relating to random variables. If you do a Fourier transform with correlation function, you get a power spectrum. And power spectrum is something that we observe, we work with, right? So in Fourier space, you have the linear power spectrum. You already saw that many times, P of K. You can also work in spherical harmonic space, where you're going to work with the observable is going to be the angular power spectrum. So once again, let's try to see. So this is, for example, this correlation function, right? Shape correlation. So you can see that here, it looks a bit nasty, but don't worry, like it's not that scary. Like once you start working with it, it becomes less and less scary. It becomes very lovely. So you have this P of K, right? And as I said, it's a power spectrum. So this power spectrum is going to be a combination with W, and this P delta. P delta is actually, the cosmology is the matter, right? It's the matter power spectrum. And this W is also very important. It's called the window function, and it has all sorts of cool stuff in it. It has a lot of cosmology. You see the omega matter, so the fraction of matter, has the Hubble parameter. And here is a very cool thing, this N of psi. So this psi is the comoving distance. So you're integrating from comoving up to the horizon. And I mean, you don't have to like know all of these things. You can try to work them out slowly. But in any case, the main point is that you're correlating, so you can observe the shear, right? You can observe the correlation or how the shapes are correlated. And you can connect it to the matter power spectrum, which is theory. But then also there is another observable here, this N of psi, and I forgot to tell you what it is. It's the redshift distribution. So maybe you don't know what that is. I'm going to show you here in the next slide, I think. Oh, sorry, it's not the next slide. Just hold this thought for a second. So I showed you here is actual results from 2018 from Troxel. So you're measuring this psi, as I said, the shapes of the galaxies. There's some distance of the sky, right? And this is, you see in arc minutes. So you're going from smaller to higher. And here is the strength of the correlation, right? If you go back to this thing, so what is telling you, the stronger the signal, the more the matter, right? It scales together in the same way, right? You have more matter, you're going to have the stronger signal. It's very, very simple to see. Okay. Here is what I was saying. So as I said, that the matter power spectrum is a theoretical part where we have our model. But then what we actually observe is these shapes, as I showed you here. So this is how the galaxy looks like originally, like really in where the light is emitted from. And what we see here is shear, right? Stretched. So we can observe the ellipticity of that galaxy. And then the other thing that we actually can observe is the redshift distribution. So that is the number of galaxies in a redshift range. And so I drew these 3 lines here. So this is the first line, if you remember from our little illustration where we had, so this is the lens, right? The big mass between us and the sources. And so this is, for example, the redshift distribution of the lenses, and then separately the redshift distribution between the lens and the source, and then up to the source, right? So we're measuring again galaxy shapes and the redshift distributions. That is what we see in the telescopes, basically. And I just showed the same equations again, just so you can see here, and I marked it here. So this is the shape, right? It's the correlation function, but it refers to the shape of the galaxy. And here is the redshift distribution of galaxies. Is everything clear so far? Daniel, are students asking you questions or something?
So far, no. There's not in the chat.
Am I clear? Do I need to repeat something else, or?
Yeah, for me it's clear. I don't know others if they have any particular question.
Yeah, students, if now is the time to ask. Okay, I'll move on. So as I said many times in this talk already, I drew like a little galaxy here, right? And these lines are just for ellipticity, right? So you can remember that this is ellipticity when it has this cross inside, like the semi-major, semi-minor axis. So we are correlating shape of one to all of the others, right? So if you remember, here is the lenses, here are the sources. So if we're correlating the shapes of this one to this one, this one to this one, this one to this one, and so on, and then this one to all of the others, right? You have to correlate all these 2-point correlation functions, right? That's what you're building, 2-point correlation function, correlation one, of pairs. So if we have a situation where we are using these shape correlations, we call that in cosmology, in weak lensing, or in lensing cosmology, is called cosmic shear. So you can do a full analysis and get answers to how much, according to cosmic shear, how much there is dark matter, dark energy, and so on, by using these correlations, right? By studying the corresponding shapes of corresponding, I should not maybe say corresponding, the correlations in shapes of galaxies in your survey. But cool thing, we have these lens galaxies, like the galaxies that are actually doing the lensing, right? The mass between us and the sources, which you can do, and a lot of people do. They match, or they're trying to do correlations between the positions of the galaxies. So basically the idea is, you can ask, if I have a galaxy here, what is the probability I'm going to have a galaxy at that spot, and so on. So you sample that again. So if you're correlating positions and positions, okay, I have a question, sorry. I will have to answer that later. Sorry, Juan. Just to stay on this train of thought. So where was I? So if you're correlating positions and positions of lens galaxies, so between lenses, you're not touching the sources, right? Just doing the lenses, you're probing the distribution of dark matter, and this is called galaxy clustering probe, right? So we have shape is cosmic shear, position is called galaxy clustering. Then of course, why not correlate the shapes of lenses and the position of, the shapes of sources and the position of lenses. You can do that, of course. And the shape position correlation is another probe that can be also studied separately, and it's called galaxy lensing. So you have 2-point correlation function of shapes, 2-point correlation function of position, and then a mix 2-point correlation function of shapes and position. So as I said, each of them can be done separately. However, it is very often that now the surveys are doing, they're combining them, because the more you get more information when you combine these 3 probes together, and because you're doing 3 times 2-point correlations, this is called in jargon, or that's why we call it, and it's called 3 times 2 points analysis. So basically, you're going to get more information about the structure of the universe because you're combining them together. Of course, I will have to absolutely say that all of these probes have problems. There is a trade-off. Like if you're doing cosmic shear, it's super cool. It doesn't have bias. I'll talk about bias in a bit. But it has intrinsic alignment. So you have to deal with one systematics. If you want to avoid that, you can just do clustering, but clustering will have this galaxy bias. So the galaxy bias is basically, would give you an equation of how the galaxy distributed, so the light is not going to basically match how your dark matter distributed, right? There is a mismatch. So you have to know how you're biased in this distribution of matter. Galaxy lensing will also have bias, but it will have intrinsic alignment problem as well, because you are dealing with shapes. So you are getting a bit better information. However, you are dealing with systematics no matter what you do, because that's the case. And we know that even if we're in an era of very precise and very, very good instruments, and telescopes are being built or gonna start working soon, still we have a lot of gaps in our knowledge when it comes to systematics. And lastly, to show you in a particular, like practical sense, what does this mean, how you are matching these shapes, right? In practical terms, when you're working with data. So you would have every group, I think, will have in in an experiment is going to have a group that's dedicated to redshifts. So these distances is very complicated issue, especially in photometric surveys like LSST. You probably, well, you know Chile, right? So you're going to have a lot of problems with photometric redshifts. So the redshift distribution, I said, is just gives you a distribution of galaxies over your redshift range. So if your Z is redshift, if you remember from cosmology courses, so every survey has a certain depth, right, up to redshift 3 or 4, depends on now what the stage 4 surveys. So it gives you a number of galaxies in this redshift range in distance. But in order to match our data or our galaxies, what we do, we slice this redshift distribution. So this is the dashed line that I showed. I mean, it doesn't look really like that, but it has a bit of a different shape. And then we slice it into bins, and we call this, it's a tomographic method, right? You know tomography probably when you go to the dentist and they have to do imaging in slices, right? So this is exactly the same concept. So you divide your redshift distribution in certain amount of bins. How you're going to divide it also, well, it's a choice. So some depend on which, if you're working with lens galaxies or source galaxies, right? They're going to probably, depending on the experiment, people are going to decide, okay, I think we should bin it in 3 or 5 or 10 bins. And I think that we should bin it in a way that they're equidistant, right? That, for example, these are not, right? So, for example, you could divide it that you have one bin from redshift 0 to 1, then from 1 to 2 to 3, and so on. Or you can bin it that you have equal number of galaxies per bin, or you can have a combination of that, or whatever you want. And what you're doing is then you're starting to correlate galaxies, so either positions or shapes, depending on which probe you're doing, or all of it, in redshift. So for example, if this is the same redshift distribution, you can do that. You have just sources, because, for example, if you're working with cosmic shear, you have one distribution of galaxies, right? It's just the source distribution all the way in the back, but sliced. And then you're doing correlations, 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, and so on. In the case of cosmic shear, you're going to have half of the matrix time plus the diagonal, and plus, it doesn't matter. Because in cosmic shear, when you correlate, it's the same if it's 2, 1 or 1, 2. Right. And then if you're correlating in the same bin, that's autocorrelation. And then if you correlating in different bins, it's cross correlation, right? So you're doing, again, for example, cosmic shear, 1, 1, 2, 1, 3, 1. So it's the same as I say here. If it's shear, it's the same galaxy. It's the same redshift distribution, just why draw it here for the purposes of understanding, right? So we're correlating the galaxies within this bin, 1, 1, then 1, 2, 1, 3, and then 2, 1, 2, 3, and then 3, 3, right? So you're going to have 1, 2, 3, 4, 5, 6 correlations if you have 3 bins. If you have 5 bins, you're going to have whatever, 15 or something, right? So
I have a question.
Yes.
I don't understand what is this. What is the meaning of correlated something with itself, like 1, 1, for example?
It's a distribution of galaxies, right? You have a lot of galaxies within this bin. For example, number 2, you're going to have a lot of galaxies. So that means you can correlate galaxies here and here, here and here, here and here, right? So that
I
means...
thought it was just one. Okay, one.
Oh, no, it's not one galaxy. It's a distribution of galaxies. There is like thousands and hundreds of thousands of galaxies in that bin, right? Because the redshift, for example, in LSST, we're going to probe up to 4, redshift 4, which is pretty deep, right? So you're going to have millions of galaxies. Yeah. So once again, for students, you're not correlating. There is not one galaxy per bin. There's thousands and hundreds of thousands of galaxies per bin, okay? So all of the galaxies in one, and then you do with all the correlations, each galaxy with, and so on. So it's a lot. So usually when you have in the papers, in cosmology papers on archive, you're going to have a similar structure here, where you're going to have I didn't include that. I'm an idiot, sorry. But you're going to have, for example, the strength of the correlation, and then you're going to have some numbers here, like 1, 1, 1, 2, 1, 3. So this exactly is showing you, they're showing you the results of the correlations per bins combinations. And often in the, didn't I put this? Let me just go back. Sorry if I'm making you dizzy. Maybe here you're going to have some indices IJ, for example, the Redshift distribution, and this is exactly refers to the case of bin IJ. Oh yeah, I wrote it here, right? Bin I, bin J. So that means exactly that. Okay, I'm going to stop sharing. I think it was a lot of information for everyone. Okay, we're going to start the second part. It's a much shorter part, I think, than the first one. Oh, what do you see? Do you see my slides or not?
No.
Just a second. Why is it not showing this? Oh, sorry. That is very strange. Where is my, here. All right, cool. Okay, hello everyone, Harold back. And let's continue with the second part of our recleansing cosmology talk. So I cannot talk about recleansing without mentioning statistics. Unfortunately, we don't have enough time, and I think it would be maybe too overwhelming for you to digest a lot of new stuff in one go. So I'll just briefly walk you through statistics. And statistics is something very important in cosmology. Basically, this is our framework. You absolutely have to do some form of statistics if you're working in recleansing. So to remind you some of the basic stuff, like if you have some sort of distribution, here is a non-Gaussian, and then you could say you have a random variable x, right? That is distributed in a certain way. So you can define a likelihood or probability. Usually they're not this, they're basically in strict sort of sense, they're not the same thing, probability and likelihood. But we can say the probability of some random variable x, right? We're going to normalize it so it equals to 1. And then you can describe your distribution by some sort of quantities we call moments. So the first moment is mean, right? The mean of your distribution is defined in this way, right? Through probabilities. And then the median of your distribution is going to be basically, where did I put it here? The dashed line here. So the median basically divides, it takes all of your measured variables, the values of your variables, and takes exactly cuts it in half. So this is the median. And then the mode is where your distribution peaks, right? If it's a unimodal distribution, right? It has one peak, so it's going to have one mode, 2, it's going to have 2, and so on, right? So this is where your derivative is equal to 0. Right, you know that in the terms of a Gaussian, and we love and use Gaussian distribution a lot. However, we have to use non-Gaussian distributions as well. But for Gaussian, these things are the same, right? The median mean. That's why I chose to draw this here. So this is something that you remember, right? So you can describe the distribution with the moments. You have higher order moments for, they're very interesting for distributions that are non-Gaussian. And those quantities or those moments are, if you remember them, maybe you had some stats class called kurtosis and skewness. So how much is skewed to one side and so on. So all of these distributions, all of these moments describe you a distribution. In case of the Gaussian distribution, as I said, we love Gaussian distribution. Gaussian distribution is fantastic. It's most often used. It's a very powerful thing. So 1D Gaussian is fully described by its mean and its variance, right? The mean is where the mean of the data is, or the mean of the distribution is, and the variance tells you how much is spread out, right? You can have two Gaussians with the same mean, different variances. So one is going to be more spread out, one is going to be thinner, for example. And then your probability, so in Gaussian terms, you can write it this way, right? Don't mind the normalization stuff. You just have the e to the, so the random variable minus its mean over 2 variance. This is squared, and then e2 minus this, right? Or you can write this exactly thing in a different way. And I want you to spend, a moment remembering this. So you have this minus 1/2 in front, then you have twice x minus mean, and then you have the variance. So remember this structure here. Okay. So what if you have two random variables that are described by some sort of Gaussian? So you have random variable x and y. So then you will have to have means, and you have to have your variances, right? So the mean is defined in this way, right? One, you just sum up all of the values of your random variable and divide by number of how many variables you had, right? If you have 50 counts of whatever numbers, 1, 2, 3, 3, 5, 5, 5, 6, 3, whatever, you sum them up all together, you divide by the number of counts, and this is your mean for x and y. Variance is defined this way, so it's you subtract the mean from each of the value, square it, sum them all up, and then divide by 1 over n minus 1. That's your variance. That will give you the spread. Since this is a two-case random variable, so you also want to see if they are correlated. So you will have to have a third thing. It's called covariance. So covariance between x and y is defined in this way. So again, you have the value of x minus the mean of x. Oh, sorry, I think I messed up the notation here. So here I put the x, the mean as with the bar, but mu is usually used for mean. So I apologize. I was just using them interchangeably, but mu is the same as the x bar, right? Is the mean of x. And this is also wrong. It should be mu x, not mu I. But in any case, the covariance between x and y is, again, the product of values of x minus the mean of x times the values of y minus the mean of y, and then you multiply it by this. And then you can construct something that's called the covariance matrix. And it has this shape. So you have the variance of x times the covariance between x, y, and then the second row is the covariance x, y, and then the variance of y. What it means in terms of data, right? If you have some sort of a spread here, some sort of data that will depend on x and y, so you can see if they're correlated and anti-correlated. So what this tells you, so this is basically, if you're thinking about, this is a 2D Gaussian. So you're looking at, of this thing, but since it's two variable, you're looking at it from the top down, right? So this is where your peak would be. So what is this telling you is also you can interpret it in this way, that if you're increasing the value of y, you can check if your x is increasing or not. So they can be oriented in a different way if they're oriented like a linear function, basically, but it's a Gaussian, right? I'm saying it's a 2D Gaussian. You're looking at it from the top. Then you can see as you're increasing the y, you're also going to increase the x, right? But in this case, it's going to be the opposite. Or they can be not correlated at all, then you would get a circle, basically, from the top. So these are the things that are usually reported one way or another in in cosmology, right? Because you want to see how two parameters of something are correlated. Are they correlated, and how much? Also, you want to see the more tightly correlated, it's going to be a thinner ellipse, right? Now, in statistics, all of you remember the two main frameworks. That there are other, but two main frameworks is a frequentist and a Bayesian approach. The frequentist approach, I think somebody told me that, and I think it's really true. Like, if you're not working with statistics, then you don't know what you are. But the moment you start working in statistics or using it, you know if you're a frequentist or a Bayesian. So frequentist approach for them, model is fixed and data are repeatable. And Bayesian is flipped, is the other way around. So data are fixed, but the model is repeatable. Both approaches are correct. There's no one way is wrong or not. The point is you have to have a frequentist approach or Bayesian depending on your problem. And usually, in most cases in cosmology, we have to use Bayesian statistics because of the problems that I'm going to show you. So what is Bayes' theorem in mathematical terms, or just written in natural language? It tells you that the posterior, so the posterior distribution of your variable x or your 2D Gaussian, whatever, it doesn't have to be Gaussian, but usually we use it, tells you that the posterior is proportional to the likelihood times the prior. So what does this mean? So your posterior is what is your model given data? And then in the other way around, so here your likelihood is what is your data given your model? And then this P of M is a prior. So it's some sort of prior knowledge that you can use. And basically you can repeat your thing over and over again if you learn something new, and you can get a better posterior. That's the beauty of it. And this P of D is called the evidence, but sometimes you don't have to use it. A very good primers I can give you about the statistic techniques in cosmology. There is a very tiny, fantastic one by Alan Havens, and then later by Lichaverde and Roberto Trotta. So I would highly recommend. But basically, this is the basic approach of Bayes' theorem, right? So again, data are fixed, but you're repeating your model. And I found a very cool example that I copied verbatim from Dragan Huter's lecture. I think I actually attended this school, ICTP school, back in a few years ago. So Dragan gave a very nice lectures on all sorts of cool stuff. And he gave an example of H0. So H0, the Hubble parameter. Let's say it's reported it's 72 plus minus 2 kilometers per second per megaparsec. So what the way the Bayesian, if you are Bayesian statistician, right? The way you would interpret this from the Bayesian point of view, it says the posterior, right, of your distribution of your H0, it goes from 70 to 74 kilometers per second per megaparsec. And this posterior can be then used as a new prior. So that means if you go back here, you can use it here as a prior and then repeat your experiment, but theoretically, right? To get a new posterior distribution. But frequentists would say, if you would repeat this procedure, it will give you the real value. So you would have to repeat. However, and then you will get the value within the 68% limit, whatever, to sigma. However, the problem is we have one universe. We can't recreate another universe and then sample again H0. It doesn't work that way, right? We only know that we have one universe. So this is a problem in cosmology, and that's why you can't really be frequentist, because we only have one universe to sample. It's called the cosmic variance problem. And probably, Daniel, you work with that. If you're working with string theory or stuff, maybe it's important to you. But that's the basic idea. And as I said, Alan has a very nice discussion about these things in his paper. It's called Statistical Techniques in Cosmology by Alan Havens. So look it up. And then lastly, how do we actually do things? So you will have to, well, you have a survey, right? You're sampling your universe the way it is. You have to have some Bayesian approach to it. But the way you're analyzing your data, as I said, you do all of these correlations, and then you can also explore your parameter space. And what do I mean by parameter space? So for example, you assume some sort of model, right? Model is a set of equations or a framework that we assume is true. And when I started this talk, I told you we are assuming a flat lambda CDM cosmology, right? That's a model. That model has a certain set of equations that describe how the things are moving around, how things are, you know, how much stuff there is, and so on. So this cosmological model has certain parameters, and these parameters I already also showed you. For example, it has omega matter, it has W naught W, that's for the gravity, for the dark energy, sorry, equational state. H is very similar. It's just the dimensionless Planck's constant, Hubble constant, sorry, Planck's constant. Then you have a spectral index. That's the spectral index of the I'm blanking, sorry, power spectrum. Omega B for omega baryons, and so on, right? All of these parameters. Sigma 8, I wrote here, sigma 8 is a normalization of the, well, it's for the density. Basically, it tells you how much stuff is clumped in the universe. Is it clumpy or not? So you can then take, for example, if this is XY, you can take omega matter and sigma 8. So omega matter should be X, maybe Y can be sigma 8, and then you can see how they're correlated. And if you're doing this, if you want to explore the full parameter space, you need to account for all the parameters that you're assuming, right? So either you need to explore them, or you can, well, you say fix them or marginalize over them. So you basically, they go into the integral. And that's part of this Bayesian thing that you can also look it up. I don't have the time to go through it. But basically what we do, you can explore the parameter space. You can explore what all of the possible values these parameters can have. Of course, with some prior knowledge. You're not going to say that, I don't know, there is whatever amount of dark matter there when we know it's less than. You can't say it's, you know, 70% when we know it's dark energy. So you have some sort of knowledge. So that's your prior. You already have some sort of prior knowledge on that. But in order to explore this parameter space, we use a technique called the Monte Carlo technique, in particular, Markov chain Monte Carlo. And there are some very cool things about it, especially this Hastings. I think Marco, who was here in the lecture, is very handy. He knows a lot about it. But basically what you're doing is you have a certain algorithm that is following. So you start from some random value of a parameter, and then you jump to a next randomly to another value. But then there is a decision process. Should you go explore more space or go back, and so on. And this is a very powerful technique. And usually when you're exploring for your experiment, you want to explore your full parameter space. However, it's very computationally expensive. So it's more correct in a way, more precise maybe, or more accurate, but not accurate, more precise. However, it takes more time. There is another way to do stuff. It's called the Fecha forecasting. And I could take 3 weeks to talk you about all of the fun and cool and terrible things about Fecha matrices and Fecha analysis. It's something that I do as well. I also do Monte Carlo, but Fecha forecasting is a neat way where you can get some answers prior to your data. So you're, in Fecha forecasting, you don't work with data at all. You can just assume your model, and you can construct an infrastructure that will compute, basically, it will compute derivatives over your models. And what you're going to get at the end are the answers to what are the errors on the theory parameters. So it will not give you exact answer, but it will give you these ellipses. Well, it's similar to this thing, right? But Fecha is going to give you ellipses, and it will tell you how much error are you going to have on your parameters if you're using this model with this certain set of. So I'm not just saying that the model has to be, it's not just a cosmological model. Also, when you're building a Fecha forecasting analysis, you need to take into account the parameters of your survey. right? Your redshift distribution, so you know what your telescope is going to, right? You're building it, so you know what the instrument is going to reach. So you know the all of these astrophysical observational stuff like limiting magnitudes or redshift distributions and so on. So you put all of these things together and you do a Fecha forecasting, and it's much quicker. It's not as reliable as MCMC, as we call this Markov chain Monte Carlo. However, it's pretty much in the ballpark. So these are the things how we usually do in cosmology. So basically, you can already have some sort of notion before you perform the experiment. And I think, yeah, I think I could recap now. So again, we talked today about the weak lensing and there's a little bit of statistics in cosmology. So weak lensing is a very powerful probe that tells you a lot about geometry of the universe as well as the growth of structure. And these are the answers what we want, right? We want to know how much of stuff there is and how it is distributed. It utilizes correlations of shapes of galaxies, as well as you can use positions of lens galaxies or combinations of them. And then we learned about these probes that are called cosmic shear, where you're correlating shapes and shapes of galaxies or source galaxies. Then you have a galaxy-galaxy lensing. It's another probe that you can use where you're using or correlating shapes of sources with position of lenses. You can do galaxy clustering, where you're just correlating the positions of lens galaxies. You can combine them together and you can do a full 3 times 2 point analysis, which is very cool. Additionally, I don't know if I mentioned that you can actually combine all of these probes. You can also combine it with voids. So voids is a separate niche, a separate part of cosmology where people are working with voids. Voids are just underdensities in the structure of the universe, right? When you look at the large-scale structure, I'm sure you've seen these wonderful images of these filaments, right? You have a large cluster of galaxies, but then there are places where there is just a little less of matter. So people are actually using these voids to do fantastic stuff. So you can additionally correlate these weak lensing stuff with the voids, and Marco, who was here, actually did that in his paper for Euclid. Then you can also combine lensing from the CMB and so on. So there are really cool techniques, and we are doing this multi-probe and trying to gain more and more information from all of it. However, of course, we have problems with the systematics, but that's a general case in every science, right? You have some sort of, you're agnostic or you're biased about some physics, underlying physics. Maybe there is something that we don't know. So we know that we know a lot, but there's still, a few % of stuff that just doesn't make sense. So you're trying to understand it and model it as much as we can. When it comes to statistics in cosmology, it's part of everyday work of a cosmologist, one way or another. The fun thing is that on large scales, the universe is very homogeneous and isotropic and kind of easy to work with. So you can assume that most of the things are Gaussianly or normally distributed and so on, or they're random. Usually, as I say, there's a wonderful completely other fields who are within cosmology who are working with non-Gaussianities and so on. Usually we have Bayesian approach. I'm not saying that we're not going to ever use frequencies, that there are other methods from different frameworks for statistics that are absolutely used in cosmology. I just mentioned Bayesian because it's so really used widely. Some methods that are very common in weak lensing, but in general in cosmology, are called Monte Carlo sampling or Fecha forecasting. There are trade-offs. Fecha is much quicker, a bit more unreliable compared to MCMC, who is more reliable, however, very computationally expensive. I think I can stop right